Hello, students. This is the third and the last topic in this chapter: memory requirements and accessing data in memories. So, we are basically looking at a C program and try to analyze how much memory do we need to execute the program. Memories in the computer systems is always limited. Therefore, we prefer to use memory wisely. Effective memory use requires a good software. When we first learn about programming, we have entered the land of chocolate. We can write as many functions, as many variables as we want. In other words, we can have as many memory that we can ask for. We can create loads of arrays, loads of data types. In terms of the data types, we can declare integers, floating point numbers, strings, using many different kinds of data structures like arrays, lists, trees, sets, dictionaries, just to name a few. In terms of control structures, we can write functions, subroutine, if-then-else loops, not to mention some more complicated object-oriented programming skills like iterators or polymorphism. However, what we have discovered so far in our module is a computer is actually quite a simple machine. Even with a machine like ARM, it's not that sophisticated. If we try to turn our view as a processor, we have only a very limited number of data types. Most of them are integers. It may be a little bit luckier if you can have floating point support. But other than that, we work with mainly integers. As a result, in terms of instructions, most of these instructions working on the data of the type integers. We have seen instructions to do arithmetic. We also have instructions for doing logic. We can compare integers and branch based on the result. So how about memory? How does the data look like if they are being stored in the memory? This is what we could have. All the data are crammed inside the processor's memory. We don't want to waste memory, therefore we try to put as much data as we could inside. It can be a simple number right here. It can be a string in the middle of the memory. This part may represent a floating point numbers. So it may look very messy to you. But as we all know, it works perfectly fine. And this is actually happening in all our programming world. The reasons for having this made possible is such a gap is being bridged by a compiler. And the compiler itself is fully automatic. We have seen already how the compiler translates our code into control flow or functions. And in this last topic, we're looking at how the compiler treats our data and put the data in the right place in the memory. Here we have a simple program with a number of different variables: integer, character, array, and some function calls. So if you ask yourself a question, what can be the possible types of data we have with this example? Quickly speaking, we could have 5 possible types. It can be the program itself. All these statements will be translated as instructions and stored as the code. Second, it could be read-only static data. The meaning of static is that it's global. It can be accessed anywhere. So it could be like this 1, 2, 3 stored in C. It can also be read-writable static data that can be changed throughout the life of the program, like A, B, D. So we also have to make sure they are well initialized. In this static data, they can be initialized, they can be zero initialized, and they can also be uninitialized. So we have seen some examples. This is being initialized, and A and B will be zero initialized. The last two will be the heap and the stack that we're going to explain in greater details later. So these are the 5 possible types. Where should they go? Code is obvious. We load these programs, the instructions in the code area, the code region in the memory map. But how about the others? How does a compiler take our information and put them in the right place to optimize the space and also optimize the speed? The first question we should ask is whether this information can change. Some of these variables, they won't change as long as the program is being provided. Like C, like the constant number 7, 29,999, these numbers that don't change. If that's the case, we could just put that in the right read-only non-volatile memory, just like the instructions. So what are the examples? It can be instructions, it can be some constant strings like hello in the program, constant operands, and some values for initializations. Examples: 31, 123. If your answer to the question is yes, then it can be changed, and therefore we want to put it in read or write memory. In our terminologies, it can be the SRAM region or external memory region in ARM space. They can be variables. They can be intermediate computations if the computation is quite long, A plus B plus C and so on. And also don't forget, it can be the return address of the instructions. The second question that we should ask is how long does the data need to exist? In other words, we're looking at the scope of the data. Some of the variables are statically allocated. They will be exist from the program from the start to the end. It has to be global. If that's the case, we would like to have each variable has its own fixed locations in the memory, so that we always know where to access. This part of the space cannot be reused. They are already occupied from the beginning to the end. Some of the variables are automatically allocated. They will exist from function from the start to the end. So when the functions finish, this space can be reused. It's likely we can put that somewhere in the stack, as we see some examples already. Lastly, it can be dynamically allocated. It exists from explicit allocation and explicit deallocations using functions like malloc or cannot that we learn in C, and the allocations we can just free the space that we have. This relies on the way the code was written, and the space can be reused once it is being freed. The key idea is we want to reuse the memories if possible, such that we can have more variables created for the application. So let's try to put our theory into the examples. So let's look at each of the variables and see where we want to put them. Let's first begin with A and B. A and B are static variables, they are global variables, and there is no explicit initializations. In C, they will be initialized to 0. Since they can be changed during the life of the program, we would like to put that in the RAM under the serial initialized data. So how about C? C is a constant character having a certain value, and therefore we can replace all occurrence of C by 123. It cannot be changed, and so we would like to put that as our constant data. And for D is a global static variable with initialized value. So it's clear we are going to put D in initialized data, but at the same time we have to prepare the value 31 in our ROM so that we know what data to load to D when the program starts. Therefore 31 will be loaded to initialized data. E is automatic variable. It has the scope with the main function. So we're going to allocate this variable in the stack. We also call that automatic variables. Similar to the array, it is only 32 characters represented by the name F, and we can also allocate that directly in the stack. Values like 7, 2, 9, 9, 9, 9, they are within the program. They are small values that we would like to put them together with the program. So we are going to load that into our instructions. So how about this string? What do you think? Is this string going to be changed? Seems not. Therefore, we're going to put that to the ROM and within the program text, similar to 7. So in C language, we have a lot of this type and class qualifiers. So it's just a reminder for you. The first one is constant. If we put const constant with a variable, that means the compiler will assume it's never written by the program, and this can safely to be put in the ROM to save our memory space in RAM. Second type is called volatile, which is in particular useful when we work with microcontroller programs. The meaning of volatile is that it can be changed outside the normal program flow at any time. It can be changed by interrupt service routine. It may be changed by hardware-controlled registers. So, putting that as a volatile will limit the compiler with optimizations. and the compiler will be very careful not to over-optimize them. Similarly, if you would like a variable to be accessed quickly, you could put register as a type modifier. And when the compiler optimizes, it will try to put the variable in registers and speed up the code. Lastly, we have static. So static is usually declared within a function, and between the calling of the functions, the variable will keep its value. The difference of static and global variables is that global variables can be accessed everywhere, so the scope is universal, but static variables has scope only limited to the function. You may want to know what is behind the scenes when a C program started. It seems a lot of things to initialize. And C compiler actually insert loads of instructions to prepare our program. So let's have a quick view on that. After reset, the MCU has to initialize the hardware with a number of different peripherals, setting up the stack pointer. In ARM, we're loading that to the highest address of the space allocated because it's full descending. After that, we have to initialize the C or C++ runtime environment. Steps like setting up the heap memory for malloc or calloc, and also initialize the variables. In particular, it has to fill the zero initialized data with zeros. So it's going through address by address, making that to be 0. We can't assume the RAM started with all zeros. It can be random numbers. Also, we have to copy from the ROM constant data or initialized data to this part, so that the data would have values from the initialized data to the RAM side. The last topic we want to look at is how we can access different kinds of variables. In particular, we're looking at either static variables, that is global, or automatic variables generated by the compiler. The key question we ask is, what does it take to get a memory variable in memory? Of course, it depends where it is. What will be the type? So if you look at this code example, we have quite a lot of different variables. Some of them is static, some of them is pointer, some of them is initialized auto variables, and this will serve as a quick example for us to see. So we take this program and we try to compile that within a C compiler, and we take a quick look on what we have inside the assembly program and see what happens with the C compiler in this aspect. So first, let's look at how we can access static variables. As we discussed, static variables can be located anywhere in the memory space, so we need a 32-bit pointer. However, we can't feed a 32-bit pointer in a 16-bit instruction or even 32-bit instructions. That's not enough information. So we need to save the pointer in a separate from the instructions, but not too far, so that we can easily access with a PC with relative offset. So the idea right now is I have the instructions to get the variable, and not too far from that we prepare the address, and this is the offset we're going to load to the PC to access the address into the registers. In the steps, we load the pointer into a certain registers, say R0, and by using this address, we can load the value of this static variable into another register, say R1. If you want to store the variable back, we keep the answer in R0, load the pointer, which is the address, into R0 and store it back. Let's look at the example. In this disassembled program, we have the instructions. We also have the address to the actual data. So you see, we have actually two variables that is being static, SIA and SIC, and within the program itself, which is this part as the area, we declare two pointers which will point to the actual locations in the RAM. So these are two separate parts by the area, data, and code that you see here, and they are separate. One in the ROM, and here is in the RAM. When we want to when the statement is being compiled, this is what being disassembled. We put the value 2 into R1. Then, based on this address, we load the pointer to the address of SIA in R2 and store the value to R2. Similarly, if you want to load the value, first we have to get the address, which is defined as a constant, to R1. Use the R1 to access the value. Similarly, to get another value and do the additions. So this will be the way that we access the static variables by using the address as the literal pool. Just to make sure, you have to remember these are actually two locations in different parts of the memory. So how about automatic variables? If you don't say anything, if you don't put any type modifiers to the variables, they are implicitly automatic. So they will be generated likely on stack. Automatic variables are within the activation record of a function, unless you force it to be the register. As we have seen before, activations records are located in the stack. Wherever a function is called, we create an activation record. When the function is returned, it would free the space. So if you look at the example on the right hand side, wherever we go from the main functions into A call into B, and so on, all the variables that declare within the functions are actually automatic variables. And therefore, they would be generated on the stack in such a way. Let's imagine we go from the main function to A. When we enter the main functions, we create local storage. We may have to say some registers. If you have arguments, they will be all loaded in the activation record of the main. When we call to A, we branch to the A, and A also declares a number of variables, and these will be created within the activation record of A. If we need to store the registers, they will be here. So these will be the record for A. We build it up. When we go to B and C, these are all added up on the stack. Since the address is from high to low, the stack grows in this way. Stack grow. So just remember, here is the low address, here is the high address. When the function finishes, we clear the activation record by making SP bigger, bigger, and bigger. So this part of the memory can be reused later on if we call other functions. So now let's look at how we can address the automatic variables. These variables are created on the stack, and therefore we need to use the SP with a certain offset to access different variables that we create on the stack. The idea is that after we enter the functions with a certain SP, we allocate the space by making SP smaller. So here is the high address, here is the low address. We may have several registers being pushed, and then we subtract SP to create the space that we need for our variables. And it would be useful that we try to create a table like this so that we know where the variables will be allocated. Once you have this allocation, the actual access of the data can be based on a constant offset with the latest value of the SP, which is right here, the N SP, and you can load the data into the register that you want. A reminder is that all the items on the stack are word aligned, and therefore every time when SP change, you add 4 to the values. 4, 8, 12, 16, and so on. The maximum range that you can address would be 1024 bytes. Why? The reason is that the offset is being encoded within the instructions and 10 bits are used. But this should be quite enough for most of the automatic variables. If you need more than that, then you need to use the heap memory instead. Looking at this example, we're putting different variables that we declare on the stack. And if you look onto the right hand side, once we enter the functions, we store the variables R0 to R3 and LR, the return address, on the stack. So they would be going from LR, R3, R2, and R1 and R0. They will be stored in the SP. And the SP will get smaller and smaller as we push. Initially, it contains the value like this. After we push 5 words, then it becomes smaller. Then we have to create a number of variables. This is auto variable. E, F, and G, they are all auto variables. So they will be created onto the stack. And what we do is after we push, we try to move the data into the registers. So what you can see is first we load the value 4 into R1, and using the offset 8 plus SP, we store the value of 4 into the locations here. And that means we are trying to initialize IE with this. Similarly, on the next 2 instructions, we are initializing AIF and also AIG using a similar manner. What you need to know is we have to make sure the offset is corresponding to the addresses we see in the table. And lastly, we calculate the additions and we store it back to AIB. And to access AIB, we have to use the offset C12 plus SP and store the value in these locations. So the last instructions that you see in this example will store the value for AIB. So it's not difficult to access automatic variables once we do a good bookkeeping on the addresses on the stack by anticipating what will be the latest value of the SP. So this will be the end of this video, and also we have a couple of advanced slides in the end of this chapter. If you're interested and have time, please spend the time to look at that and complete the assignments and lab exercise related to this part. Thank you for your attention. Bye for now.